purpose of power hardening the simulation. So why we are using
Pessoal,
and welcome to my presentation, Benefits of Power Hardware in the Loop Testing. My name is Biljana Sovil. I work for Egston Power Electronics, and here at Egston Power Electronics we are producing power amplifiers, so basically we are providing power for your real-time simulation. My presentation will be focused on understanding what power hardware in the loop is and what are the benefits of power hardware in the loop simulation. I would like also to tell you that I'm glad that I have a chance this year to participate at Sepoc conference. This year it is online, but I hope in the future I will have a chance also to participate in person. So let's slowly start with the presentation itself. So the first thing that we need to figure it out is the purpose of power hardware in the simulation, so why we are using it. So the purpose of power hardware in the loop simulation is to facilitate the study of closed loop interaction between different components of a different system of interest without having a need to create entire system in the real world. So when should we do power hardware in the loop simulation? So the answer is as soon as possible. So what does it mean? It means that you should start as soon as hardware of interest or prototype is available, no matter whether you are creating a new system or you are working on upgrades of existing one. Power hardware in the loop simulation should not replace testing of entire system of interest unless such testing is not practical due to the cost, risk, schedules, etc. So let's first start with the basic definitions of terms that we will use through this presentation. So what is hardware in the loop at the first place? Hardware in the loop is technique that allows closed loop interactions between hardware of interest and model of interest using real-time simulator. So as you can see, there are two parts of system, hardware of interest and model of interest. As I just mentioned, here is a technique that allows interactions, and there are two types of interactions that we can have. Power hardware in the loop and control hardware in the loop. Both doing closed loop interactions between hardware of interest and model of interest, but in slightly different way. So in power hardware in the loop, we all have hardware of interest and model of interest, but natural couplings and the power interfaces that exist in the system of interest is intended to be preserved. What does this natural coupling means? In simple words, it means that instantaneous power on power interfaces of hardware of interest is preserved. So with doing power hardware in the loop, we are preserving also these natural couplings and providing instantaneous power, current and voltages that hardware will actually work with. And this is the main difference compared to control hardware in the loop, where instantaneous powers are not preserved, but in this time of simulation we are communicating on a signal level. So controller hardware in the loop is where there is hardware of interest interface at the signal level to the model of interest, where natural couplings is not intended to be preserved. So where do we see power hardware in the loop in terms of fidelity and flexibility? Basically, here at this slide you can see that we can have computer simulation, control hardware in the loop, power hardware in the loop, and system testbed. And we observe these different configurations in terms of feasibility and fidelity. Pure simulations, of course, has widest test coverage, but test fidelity is not as good as we are relying purely on simulation. And models have its own constraints, which leads to low fidelity as a result. The controller here has slightly lower test coverage, but has a little bit higher fidelity as you are involving controller simulator and you have actual real controller involved in the testing. The next thing is presented is actually a huge step towards fidelity of testing, and it is testing in power hardware in the loop environment. Because by doing power hardware in the loop testing, you are preserving these natural couplings that we have mentioned in previous slide. And this will slightly decrease test coverage, but by preserving natural couplings, we are drastically increasing test fidelity. Of course, you have to take into account the limitations of power hardware in the loop system and power amplifiers when it comes to the bandwidth and accuracy. And last thing is system testbed. System testbed provides the best fidelity, but downside is that is typically developed for few dedicated applications, and it doesn't have this wide coverage of test cases for different applications because it's usually built for a specific purpose. So let's now go to the power hardware in the loop basics. And this block diagram shows how power hardware in the loop setup looks like. You can see that on the left-hand side we have power hardware in the loop software. On the right-hand side, power hardware in the loop, and in the middle we have power hardware in the loop interface. Hardware of interest is part of real hardware that we want to test. And model of interest is model that is running of power hardware in the loop software. We will be focused today on power amplifier part of the block diagram, and as this is topic of our today presentation. Power amplifier plays important role and has huge effect on overall performance of power hardware in the loop simulation. It has certain characteristics, certain imperfections and limitations, and we should be aware of these limitations, for example, limited bandwidth and limited accuracy. First of all, model of interest needs to be able to replicate all instabilities of the system. So in the case system has certain instabilities, those instabilities should be preserved and replicated by a model of interest. Second thing that should be taken into account is, as I previously mentioned, imperfections and limitations of power amplifier. And of course, people who are using power amplifiers should be aware of its capabilities and limitations. So, if power amplifiers due to their limitations can cause certain instabilities during simulations, those should be known and taken into account or sometimes even avoided. So for example, there is certain frequency range that we know that have stability problems. This should be avoided during the simulation process. So what needs to be done before simulation even starts? So there is a certain checklist that we could use and certain things that should be considered. Maybe this list looks like straightforward and a common sense, but I think it doesn't hurt if you just before doing simulation consider what is there to be taken into account. So, as I mentioned, power hardware in the loop simulation should consist of at least one hardware of interest in close interaction with the model of interest simulated on a real-time simulator. Before establishing power hardware in the loop simulation, users should determine which part of the system exists as a hardware of interest and which parts exist as a model. Such a power hardware in the loop simulation should represent an entire system of interest. The interfaces between hardware of interest and model of interest should be chosen in a way so they minimize their effects on the anticipated results of scenarios studied via such a power hardware in the loop simulation. Since effects of the interfaces cannot be eliminated, these effects should be characterized properly and documented along the results obtained by power hardware in the loop simulation. To perform power hardware in the loop simulation, the simulated portion of the system model of interest should execute in real time at simulation time step size that is adequate for the purpose of study. All time-dependent variables in the model of which should update in synchronism with the real-time on a real-time simulator with appropriate accuracy required for the application. So, based on previous slide, which was quite theoretical, that comes a question, okay, but how should I do this practically? How should I select my power hardware in the loop setup for my applications? In order to determine that, we can use this system simplified model of our entire system that you can see on this slide. So on the left hand side, you can see real-time simulator and controller algorithm that is executed there. You can see that we have a PI controller. Block marked at green represent power amplifier part, and in between you can see block that represent transport delays that represents models of delays of set points coming from real-time simulator to the power amplifier, as well as the delays of a measurement signal from the measurement system back to the real-time simulator. So we will use this model and these things to determine how to choose right components, right parts of our power hardware in the loop setup in order to have, of course, meaningful and successful simulation. So, first thing is that we should define its bandwidth of model of interest. This is one of very critical points which is pretty often not done properly and can cause problems later on in the simulation process and modeling. So what is actually model of interest bandwidth? This is actually the highest frequency that should be controlled in a closed loop. And then the question is how to select it. The critical thing is that this is not fundamental frequency of the system. And here you can see examples on how to select frequency. So for AC applications, the frequency of highest order harmonic to be represented by the model. In case of impedance measurement applications, the highest perturbation frequency to be tested. Electric machine simulation, the highest frequency at the back of VMF to be models, or the higher frequency of the machine torque ripple, or highest frequency of the currently ripple generated by a converter driving the machine, whatever is higher. So you are basically aiming to find the highest frequency that could appear in your model of interest. Once we know what is the highest frequency that should be taken into account, what is required bandwidth, we also need to define what is the quality of the signal that we would like to have, or that is required by model at the model bandwidth frequency. This is pretty important because this determines accuracy of your simulation. From these pictures, you can see that you have set points in different granularity, and it is better if you have more set points during the period of signal of interest at bandwidth model frequency. So you can see that there is a representation of analog signal, shown here in blue, of the model is much better if you have more set points, so instead of 10, 25 samples, for example. So for this kind of evaluation that we are doing today, we will assume that we are going with 25 samples, or at least 25 samples, but of course you can also go with more, for example 50 or more. But let's say for this example that we are doing today, we will take 25 as a good measure. So once you have defined output quality at F model max, then we need to determine model cycling time. This is pretty simple and it is done just by taking into account that we want to have 25 samples and corresponding F model max. So for this we use the following equation and the result will be model cycling time. Once you have model cycling time, you need to determine what has to be real-time simulator cycling time, because of course your real-time simulator must be able to send these set points and process measurement values during this cycling time. So really simple way to estimate real-time simulator cycling time is to make it lower or equal than model cycling time. In that way, your real-time simulator will be able to execute model within required cycling time. Now that you know cycling time for your real-time simulation, the question is, how do you select actual real-time simulator? And the question is also like what is available on the market. So typically there are two technologies for real-time simulators, and one is CPU-based and the other one is FPGA-based. So from the table you can see short overview of main properties of these two approaches. So in general you can see from the table that CPU-based simulators are a little bit slower because they have higher cycling time, and FPGA-based are faster, but handling of CPU-based simulators is easier because model compilation is faster. You typically do not need to have any coding experience. Code generation is typically automated, and you can use simulation languages like MATLAB. On the other hand, in general, FPGA-based simulators require some coding experience automation is not so good and you're lacking support, but they are much faster. So what should I choose then? So basically, based on technologies, and technologies are constantly evolving, we could use 4 microseconds as a reference point or a base. So if your time step is less than 4 microseconds, you should go with FPGA-based approach, and if it's higher, you should choose CPU-based. And of course, there is an overlap between these two. Now, when we have determined this, we should determine what should be the properties of power amplifiers. So we determine what is desired bandwidth of the model, simulation time step of the model, quality of the signal time step of a real-time simulator. But in order to perform power hardware in the loop simulation, we also need to add power amplifiers to the whole story. So what should be the properties of power amplifiers so you can actually simulate this thing you want to simulate considering the model bandwidth? And the good practice is to select power amplifier whose bandwidth is 50% higher than model bandwidth. And this is design guideline number 6. Once we know that, we need to figure it out the stability of the system. We need to know what is required to make our system stable. In order to assess stability of the system, we can do that by checking system open loop transfer function. In first slides, if you remember, we represented power amplifiers as a simplified first order function. And if we assume that phase margin is 60 degrees, which is pretty good engineering practice, that would mean that we have phase shift of 120 degrees. Then you can see that this transfer to open loop delay time looks like this. And we can see that open loop delay time consists of delay time between real-time simulator and input of amplifier, then delay time of amplifier itself, and delay of measurement system. So based on this, we can conclude what is needed to be done from amplifiers. Based on what we have discussed previously, we can now take a look into this power hardware in the loop selection diagram, which is pretty simplified, but can be a good tool or a good starting point to determine what is necessary for your power hardware in the loop setup and your applications that you want to test. Of course, later on you can replace your simplified first order function representation of your power amplifier to more complex one, more realistic model of amplifier, but as I said, this can serve as a good starting point. So let's say, for example, we have model whose bandwidth is 2 kHz. So how I determine the rest of the values? And the rest of the values are power amplifier bandwidth, what is model cycling time, and open loop delay time. So we can get this just by checking these cross sections. So for model bandwidth, for the model whose bandwidth is 2 kHz, we would need amplifier with 3 kHz bandwidth. Model cycling time should be around 20 microseconds, and open the loop delay time should be less than 167 microseconds. So this is like a first step that you can do in order to determine what is power hardware in the loop system that you need so that you can successfully simulate your system of interest. So on the next slide, we will see how do we see power applications when it comes to the frequency and power levels. This is just an estimate based what we've seen by now. So we split applications in different groups and we based on power levels and bandwidth. So you can see here some of applications which are grid-related applications, wind and solar, electric power trains which require higher powers and slightly, let's say, lower bandwidth. And we have various power converter applications and low power automotive and aerospace applications which require low power but higher bandwidth. Okay, so now let's just see what are benefits of power hardware in the loop simulation. The simplest and first thing that this can reduce cost, especially when it comes to the very complex system, because testing can be much simpler and much cheaper in power hardware in the loop environment than testing the entire system. Also, the risk failures. Complex systems in edge operating conditions can be tested using power hardware in the loop to reduce the risk of catastrophic equipment failures and safety hazards. What is really helpful and you can do is in power hardware in the loop environment is to have simultaneous development of different components of the system. So for example, you're developing electric machine for EVs and electric inverter. You can simulate, for example, inverter with power hardware in the loop and have physical machine available. Or you can simulate the machine with power hardware in the loop and test inverter against this simulated machine. Besides that, you can as well test different inverters on different power levels. And in the case you do not have power hardware in the loop setup, in order to do these kind of tests, to test these different inverters, you will have to have several motors of different level groups with different power levels. And all of this can be replaced with one power hardware in the loop system that can be simply configured by changing different parameters. And this simplifies significantly this task and also reduces the cost. And the last thing on the list is also really important, and this is the testing of fault modes, which are typically really impractical to test with a real system. And with this, we came to the end of my presentation. I hope you enjoyed it. I hope you learned something new and that this presentation will help you in the case you need to choose your power hardware in the loop setup, and that I managed to communicate benefits of power hardware in the loop testing. I hope you will enjoy the rest of the Sepoc conference and hope to see you all soon. Bye!
Elder. I would like to invite to come here, ladies and gentlemen, Dr. Elder. It's with great pleasure that we welcome the speaker, Dr. Elder Tavares Câmara, with his lecture titled Risks and Challenges to Develop High-Efficiency Systems for Legacy Industries. Elder Tavares Câmara holds a degree in electrical engineering with an emphasis in electronics from the Federal University of Santa Maria